So we've looked at computing likelihood ratios to compare two completely specified models, either when the data are discrete or the data are continuous. And so hopefully it's clear to you that the intuition is that if the likelihood for one model, that is the probability of the data under that model, is bigger than under another model, then the likelihood ratio is in favor of that model and the data favor the model. In other words, the data favor whichever model is more likely to lead to those data. So that's the intuition, and now we're going to see if we can say a little bit more about, well, you know, how big a likelihood ratio is, if you like, convincing us that one model is the truth compared, or at least a much, much better bet than the other model. So that's in this vignette here, this one here, like LRMBF. Okay, so the vignette starts by kind of reviewing the things we've already seen. So remember, we saw two examples, one where we looked at classifying a tusk as coming from a forest elephant or a savanna elephant, and we put together two models and we computed a likelihood ratio for some data, and we came up with a likelihood ratio of 1.8 in favor of the tusk coming from a savanna elephant. And then in the second example, we looked at an example where we tried to classify an individual as being diseased or normal, and we had two models for levels of a protein in the blood, and we computed a likelihood ratio. In that case, the likelihood ratio was 14 to 1 in favor of the diseased case. So I mentioned before that the likelihood ratios kind of have a human scale to them. So I guess the idea is that, you know, 1.8, well, that's definitely evidence in favor of the savanna, but it's not super convincing, it doesn't seem. And one way of thinking about that is if, you know, if someone came in with a very strong expectation that actually this was from a forest elephant for other reasons, that the DNA evidence maybe wouldn't be enough to outweigh that. That's an idea we're going to quantify in a minute. For the disease case, I think we can all agree that 14 is bigger than 1.8. So the evidence in that example is stronger, but is it enough to be convinced that the individual is diseased? Well, again, the idea is that that depends on what we know about the relative plausibility, if you like, of being diseased versus normal. So in a setting where you're testing for a very rare disease, and so where most people you're testing maybe you know that most of them will end up being normal, then in that kind of context, a 14 to 1 likelihood ratio might not be enough to convince you that the person you've tested is diseased. Whereas if you're testing for a common disease and most of the people you're testing are diseased, then 14 to 1 might be quite convincing. So the issue here is that context matters, and so you have to combine the information in the likelihood ratio with what you know about the relative plausibility of those two models that you're comparing. So that's where this vignette is going. Just to mention a piece of terminology here, you can see at the top here that if I just, I think I can spotlight there. Here the Bayes factor. Bayes factor is just another name for likelihood ratio when you're comparing two fully specified models. People sometimes use the terminology differently in cases where parameters have to be estimated, but in the case we're looking at here, where the models are completely specified and there's no free parameters, that is, you know, P of X given M1 and P of X given M0 are completely specified by M1, the models M1 and M0, then the Bayes factor is just another name for the likelihood ratio, and I'll use those two terms interchangeably. Okay. So, so if we go down here, the basic tool that we're going to use for doing these calculations is Bayes' theorem. So I hope you all recall Bayes' theorem. Maybe I can give you a quick reminder. Bayes' theorem is P of B given A equals P of A given B times P of B divided by P of A. Okay, so it's Bayes' theorem. And so we can use this here to do the calculations that we want. So in this case, we want to compute the probability that, for example, MS is true, that is the savanna elephant, given the tusk data, which is X. And so just plugging those in, we get that that's equal to this expression. Okay, so we're just using that expression here. If I go to, oh, that's the wrong place. There we go. All right. So in this vignette here, that just go through the calculations here, and actually, I guess this particular example is the diseased example, but it's the same idea as the savanna or forest elephant example here. And so we use Bayes' theorem here to come up with an expression for what's the probability of the individuals diseased. And here the two key things here are the likelihood ratio for being diseased versus not diseased, which we've already talked about, and the prior probability of being diseased versus not diseased. So pi1 is the prior probability of being diseased, and pi0 is the prior probability for being not diseased. So think about a setting where you're screening a whole series of people, and then some of them are diseased and some of them are not diseased. And so pi1 here is the proportion of those individuals that are diseased, and pi0 is the proportion that are not diseased. So of course, it could be that you don't know what those numbers are, but for now, that is, you might not know what the frequency of the disease is in the population. But for now, let's just assume we do know that, and then we can do these calculations. Okay, so in this example, so I think you can just follow the algebra here, which is Bayes' theorem, and then we can plug some numbers in. So in this case, with this example here, plugs in the numbers if the likelihood ratio is 14 and 5% of people have the disease. And if we put those numbers in, we see that the posterior probability, this is called the posterior probability because it's the probability after, posterior means after seeing the data. Maybe I should have said, I used the word prior probability before. Prior means before seeing the data. So before seeing the data, 5% of individuals are diseased. And this is having observed the results of that test, having observed X, what's the probability that this individual is diseased? Having seen a likelihood ratio of 14, and we see that the answer is 42%. But it's crucial to see that this calculation depends on that proportion of individuals that were diseased. If in contrast, 50% of people have the disease, then a likelihood ratio of 14 would yield a posterior probability of 93% here. So the intuition here is that how confident you should be after seeing the result of this test that the individual is diseased will depend on how confident you were before you did the test, or particularly on how common the disease is in this case. So the intuition is if the disease is pretty common among people that you're doing the test, maybe before you did the test it's 50-50, then a likelihood ratio of 14 is reasonably convincing. You're 93% probable after seeing the data, that after doing the test, that this individual is diseased. Whereas if you're if beforehand you have reasons to be skeptical that the individual is diseased, maybe most people are not diseased, then a likelihood ratio of 14 might not be enough to outweigh that. So in fact, in this first example here, a likelihood ratio of 14 still wasn't enough to convince you that there was more than a 50% chance that the individual was diseased. Okay, so that's intuition. The calculations here just involve simple application of Bayes' theorem, but there's a slightly different way of laying out the calculations. It's the same calculation, but a different way of laying out the calculations that's given here. So maybe it's, I think it's worth just taking a look at this. So this is just Bayes' theorem here, applied to the posterior probability that the individual is diseased. And this here is also Bayes' theorem applied to the posterior probability that the individual is not diseased. And the idea is that you can simply take the ratio of these things, and that leads to a nice cancellation. Specifically, this probability here, which is the probability of the data, which is a little inconvenient sometimes to deal with, cancels out, so that when we get the ratio, we get a nice formula here that also has a nice verbal expression here, which is that the posterior odds is equal to the prior odds times the likelihood ratio. And this verbal expression can be useful to keep in mind and help you do some calculations in your head and get you the intuition for what's going on. So let me just take you through what these terms mean. Odds is used in statistics to refer to the ratio of two probabilities. So that's all that it means. The odds are just the ratio of these two probabilities, the probability that z is 1 versus the probability that z is 0. And it's called the posterior odds because this ratio is conditional on x, conditional on having seen the data. On the other side of the equation, you can see the prior odds, which is exactly the same probabilities, but before you saw the data, just the ratio of being diseased divided by the probability of being diseased divided by the probability of being not diseased. And then this final expression here, which is the probability of x given z equals 1 divided by the probability of x given z equals 0, that's the likelihood ratio that we've already seen. So that's what gives you this idea: posterior odds equals prior odds times likelihood ratio. And the nice thing about this expression is it very succinctly and explicitly shows you how both the likelihood ratio and the prior odds combine to give you your posterior odds. So let me just give you an example. If the prior odds, if we know the disease is 5% of individuals are diseased, so the prior odds is 5 to 95, or roughly 1 in 19. And the likelihood ratio is 14. So I can do a posterior odds there, which is 14/19, which I know is just less than 1. So I can already tell in my head that the posterior odds is just less than 1. And so if the odds are just less than 1, the bottom has to be slightly bigger than the top. So in other words, it must be slightly more probable that the individual is normal than diseased after seeing the data. And just more generally, so a posterior odds of 1 would mean it's 50-50 after seeing the data. So another way of thinking about it is if the prior odds were 19, you need a likelihood ratio of 19 to cancel out that prior odds and give you a 1-to-1 posterior odds, which would be 50-50 after seeing the data. On the other hand, if the prior odds were 1, that is, if I'm 50-50 before seeing the data about the individual being diseased or not diseased, and I have a likelihood ratio of 14, then I can immediately see the posterior odds is 14-to-1, which I can see, well, that's bigger than 10-to-1, which would be roughly 90% posterior probability to 10% non-posterior, 10% probability of being normal. So you can see that I can already see it's bigger than 90%. And as we saw, in fact, earlier, it was 93, right? So it's here. So this formula here, this way of thinking about it, posterior odds equals prior odds times likelihood ratio, can just be a convenient way of seeing that the likelihood ratio is kind of being weighed against prior probabilities in order to decide on the posterior probability. Maybe we could even just think about, spam data, spam email, trying to classify emails as spam or non-spam. So let's suppose we have a likelihood ratio of 100 for an email being normal to spam, let's say. So a likelihood ratio in favor of being normal, being ham, of 100. Let's suppose that 1 in 10 emails is, or maybe 1 in 11, to make the calculations a bit easier, are really ham. So in other words, the prior odds are 1 to 10. So I can do one in my head, I can do a 10th times 100 gives me a posterior odds of 10 to 1, or roughly 91% to 9% of being ham versus spam. So again, you can kind of it's kind of good to have this idea that you're weighing, your likelihood ratio gets weighed against the prior odds to give you the posterior odds.